This first module introduces software engineering discipline as an overview. So we'll present basically the course material in one lecture, and then we spend the rest of the 14 weeks explaining this one lecture and having you guys live the experience through your class projects. As usual, we have outcomes for the module. At the end of the module, look them over, convince yourself that you can do these things. If not, then go back, review, listen to lectures again, look at the notes until you feel like you're comfortable having these. I always recommend being able to explain this to another person. That's how you know when you know something. So, what is software engineering? A lot of words on this page, so I won't cover all of it. But a couple of different definitions, and you can look at what the similarities are and the differences between them. So we say, okay, the Bauer, 1972, the establishment and use of sound engineering principles in order to obtain economically software that's reliable, works on real machines. So this sound engineering principles, no matter what field of engineering you're in, there are engineering principles related to that discipline. Engineering is a lot about process. We're going to talk a lot about process in this course. For 1990, software engineering is that form of engineering that applies the principles of computer science and mathematics to achieving cost-effective solutions to software problems. I think we're going to see later on in this lecture that's a little bit one-sided. It leans a little bit maybe too heavily on computer science and not enough about how to manage teams or how to run a business or how to determine that you've got good quality software. IEEE 1993, the application of a systematic, disciplined, quantifiable approach to the development, operation, and maintenance of software. So in this one, this systematic, disciplined, quantifiable, those are sound engineering principles. It's another term for that. This one brings in the notion of maintenance of software, which is a huge topic that we don't get to address too often in academia. But software systems, they get deployed into the real world, and then they exist for 5 years, 10 years, 20 years, 30 years. They have to be maintained all that time. In fact, a maintenance contract over the lifespan of some software might be far larger than the original contract was to produce the software, in terms of effort and cost or income to the company. How does computer science and software engineering relate to each other? The one-liner I like to use is this: computer science basically asks the question, what can a computer do? We've got this thing called a computer. What can it do? What are its limits? What computations can be performed? And then once those questions are answered, the software engineer says, okay, now we know what a computer can do. How do we use it to make good products, specifically software products? So software engineering is a real blend of the programming, algorithmic, theoretical computer science stuff and the kind of process stuff that business managers need to know. This class is going to focus more on process. I should also add, since the software engineer has to have a foot in both of those worlds, they tend to be less knowledgeable in depth about the pure computer science aspects and more knowledgeable than a straight computer scientist would be in terms of process, teaming, product development, product definition, these kinds of things. Okay, so if we're going to focus on process, what's a process? A series of steps involving activities, constraints, and resources that produce an intended output of some kind. You have a process for how you study for a test. Certain activities that you do. Review the homework, do extra problems, talk to friends, gossip about what might be on the test. And then you have constraints. You're taking 4 or 5 classes this semester. You probably have time constraints. You probably have constraints that if you don't understand something, you may not be able to get ahead of a hold of a professor or a tutor in time to ask the question. And then you have resources. You have textbooks. Sometimes you have previous exams. You have homework problems. You have example problems that were worked in class. Your tutors, your classmates, the professors. Those are all resources. You have the internet. And then you produce some intended output. Ace that test, right? That's the intended output. So you have a process for that. Whether you know it or not, you have a process. It's a good idea to know what your process is. So when you have a process for how you're doing your schoolwork, be aware of it. And that way, if you're aware of it, if there are parts of it that are weak, you can work to fix those. Now, there's many software development models have been developed over the years. Linear and sequential, waterfall, the agile, which are many variants. That's the one we'll focus on in this class. Prototyping, spiral model, V model, component-based design, all kinds of different development models exist. We'll talk about a grouping of these towards the end of the semester to give you some awareness of different models, but for most of the class we're going to focus on the Agile model, specifically Agile Scrum. Some more thoughts about software engineering. Some people claim that software engineering is a subdiscipline of systems engineering. Now, what the heck is systems engineering? Systems engineering is when you take components, often that were created independently by people, and combine them into some kind of a system. You probably don't think of your car as a system, but it is a system. It has an engine, a fuel system, a drivetrain, a steering mechanism, comfort mechanisms like seats. All of those things have to be put together into one working car to make a system. So think about software systems. If we think about a automatic teller, ATM, that's a system. If we think about navigation guidance system for space station, or think about GPS that aircraft use and now our automobiles use. Flight support software for Boeing 77. By the way, the Boeing 77 has, I don't know, somewhere well over 1 million lines of code. Right. Airplanes used to be things that fly. Then they were things that flew with computers. Now they're computers that fly. Baggage handling, Linux operating system. Notice how many of these, by the way, have a software component and a hardware component. That's where you really get into system. So making sure your software is good in and of itself doesn't make sense sometimes unless you can make sure your software is good working with the hardware that it's supposed to work with. In this class, we'll almost certainly have a pure software system for your projects, but some of you may have projects that you want to interact with mechanical devices. A goal of software engineering: quality, software, on time, within budget, and the old joke says, good, cheap, and fast, pick two. In other words, there's inherent difficulties in these things. If somebody wants the product fast, you don't have time to develop it as well as you'd like to. You don't have time to test it as well as it'd like to. It may not be any good. It certainly won't be cheap because you got to throw a lot of people at it. You can have it good and fast, but that means you have to put even more people on the project, so it's not going to be cheap. There's this inherent tension between these three things, and the trick is to find a good balance so that you can produce software or software hardware systems that are economically feasible, where people will buy them, and yet good enough that people want them, and timely enough that you can bring them to market. That's particularly true, by the way, in the gaming industry. Talk about fast, right? They really have to get product release out before the Christmas rush, before the other game companies get their games out. They really focus on the speed of delivering that product. This brings us down to a software engineering framework. You can think of these things as different layers that you have to worry about: the tools, methods, processes, quality focus. The foundation has to be quality focus. If you don't have good quality, everything else doesn't matter. You've all worked with buggy software. You've all worked with lousy software. You've probably, now that we have app stores and we can download things to our phone, usually there's multiple apps that do the same job. And you download an app and you don't like it, it's buggy, it crashes, it makes your phone run slow. So what do? You ditch it, you go back to the App Store, you find a different one. So if you don't have quality, the other things don't matter so much. In order to achieve that, you need a process. Now, when you get hired in industry, the company will tell you what their process is. In this class, I'm telling you what the process that we're going to use is, Agile Scrum. You can develop your own processes, and there's a number of them out there. Again, we'll discuss. Methods. Okay, now that you have a process, how do you actually go about your day-to-day work? What are the methods by which you develop the design, by which you're going to document the design, by which you're going to do the testing? How are you going to take that process and actually bring it into the real world? And then lastly, tools. And of course, tools change all the time. So a lot of you have already used Eclipse, that's a tool. You might use GitHub, that's a tool. And tools change. A language is a tool. Programming in Java versus Python versus something else. These change all the time. The underlying processes are slower to change, but you can take that same process and apply it to a Java project where you're building something in Eclipse, or a Python project where you're just using the raw compiler. The same processes could apply to either of those tools. All of those have to be addressed when you're doing something commercially and academically. Now, the good news is, in terms of academics, a lot of these things are handed to you or suggested to you. And as a summary, here's some websites you can go to. I recommend at least perusing these things from time to time, particularly if you're a software engineering major, you should be aware of these things. These things do provide not just good information about what software is, they have information about latest techniques, they have information about, one is about ethics and professional practice, and they have information about what kinds of skills you might need to know if new things come along, new skill sets. Cybersecurity is a very hot topic these days. What kinds of things you're going to want to focus on. And then they give you resources to industry standards, often papers published by people who have done some work, learned something, and want to share it with the world. These kinds of things. Okay, so there's an overview of just a high-end overview of what software engineering is about. The next section of this will talk about problems, things that prevent you or challenge you to get quality software out the door on time with a good cost.